Let's look at how you can graph a derivative of a function when you don't actually even have its equation. Now you can do this just by looking at the nature of the function that you're examining and looking at the gradient of the curve at various points. And you can then draw a graph of its derivative. Obviously the labels will be quite different. Here as an example I have a graph of temperature over time. So I have temperature with a big T as the y-axis, and I have time in hours as a little t on the x-axis. Now when it comes time to graph the derivative of this, which of course will be dt, where we have the big T being temperature over the little t time, the way to figure out the notation for this is just to remember the advantage of this dy dx notation that we've already seen is that it tells you what to differentiate with respect to what. So if you're looking at temperature over time, then you'll have the differentiation of the temperature with respect to the time, and that tells you what units you have. So a lot of the questions that we'll be doing from now on, instead of having y and x, often we're graphing something like population, which might be a large P, or mass, which might be a large M, and because we're often looking at a rate of change, we're often looking at t on the x-axis because we're seeing how some parameter changes over time. So this is something that we're going to see a lot of from now on. Now, some steps to graph our derivative function. We've called it dt, so you'll notice that I've labelled my y-axis over here, dt, and the units on my x-axis are actually the same as the units on my actual function. Now, the first thing I do, I've written it as step 1, is I look for stationary points on my original graph. And these are the points that have a horizontal gradient. So that tells me that the derivative there must be 0. So over here I can see that I've got a flat point on my curve up here, where the gradient will be 0. So I can put a great big 0 on top of that. Now if I'm graphing the gradient and I can see that it's 0 at 3 hours, then down here at 3 hours I can put a dot, and that helps me know what it's going to look like there. It's definitely going through this point. At this point, this would be the only part of this graph that I have. Step 2, I note where the gradient is positive or negative. And I put symbols on my curve. Now I've found that if I just look at the gradient, and it's helpful to use a pen or something like that, just sit it on the graph and you can think, well, that's a positive gradient, says that, says that, says that. So these are all positives. And I've placed a bunch of little positive symbols there. You'll see that I've made a big positive symbol where I think the gradient is the biggest. So this might be a gradient of, say, I don't know, something like 2/3. Whereas up here I might have a gradient of like 1/10 or something really tiny. So I can see that the gradient is positive up here, but it's getting smaller. So I like to mark this with a big plus and then progressively smaller pluses until the gradient's 0. Now putting my pen on the curve around here, I can see that in all of the rest of the curve, the gradient is actually negative. Now how negative is it? Well, when it's at its steepest point there, I can see that it's most negative. I mean, this gradient could be something like, I don't know, -1. Looks about 45 degrees, doesn't it? Whereas up here, it might be something like -1/10. So it's clearly going down, maybe -1/2, -2/3, -3/4, until it's -1. And then after that, it gets flatter again. So it's going back into smaller negative numbers, in other words, slightly bigger numbers. So I've put a great big negative symbol here where I think it's the steepest, and I've put progressively smaller negative symbols as it flattens off in both directions. And here I need to think about the fact that it's only a very, very tiny negative fraction here. It's almost 0, isn't it? But we can maybe hypothesize that it's tending towards 0 if we were to keep graphing it. So what do I do with those symbols? Well, I think about where my curve's going to be. So it's positive from here to here. That tells me I need something of a line up here. It could be curvy, it could be a line, I'm not quite sure. And I know that it's going to be below the t-axis. Think of the x-axis as the t-axis now. Now if this is 0 here, these are all negative numbers, aren't they? And these are positive numbers. So if our gradient is negative from 3 onwards, then our derivative will also be negative because it really is representing the gradient, isn't it? Now, what do I do with this point that is the steepest point? Well, this point here is called a point of inflection. So that's my step 3. I spot any points of inflection on my curve, and this is where the gradient is changing concavity. So, well, the curve itself, I should write, the curve is actually changing concavity. And we can see that the gradient is doing some funny things. If I put my pen on this graph and move it along, you can see that my pen is basically sort of rotating clockwise, isn't it? But when it gets to that point, it starts to rotate anti-clockwise after that. So that change where your gradient goes from moving one way to moving the other way is a point of inflection. I'm going to write here P-O-I. Now we've seen these before when we looked at a curve like, say, y equals x cubed, and we already called this a horizontal point of inflection. So remember, points of inflections can be fully horizontal. And same thing, the way we define them, well, you can see that this part of the curve here is concave downwards, and this part of the curve here is concave upwards. And so the concavity is actually changing. And you can identify it again with your pen. Here it's moving clockwise, but from there on it's moving anti-clockwise. So that's a good way of spotting your points of inflection. Now, these will be stationary points on your graph of the derivative. Now, let's think about why that would be. Well, if we're graphing the derivative, we've got a small negative number, but eventually it gets to the biggest negative number it's going to get, in this case maybe -1, and then it starts increasing again, doesn't it? When I say increasing, it will be a smaller fraction, but it's a negative fraction. So the gradient's clearly dropping here until it gets as low as it's going to be, and then it starts increasing again. It's still negative, but it's increasing. So that tells me that here at 6 hours, the gradient is as low as it's going to get. And that gives me something of a turning point there, or a stationary point. From here on, I can sort of assume that the gradient is leveling out if I was to keep graphing it. So it's tending towards 0, but never seeming to quite get there on this section of the curve. So I can sort of draw in a curve like that.